small shop owner has died in the Santa or in any Raitu Bazaar.
Those type of plastics are known as thermosetting plastics. Comparison, there are 3 types.
Up, down, right, left.
I am not inferior to anyone.
Dear Flores, you're top on the hour. Congratulations.
I want to be a leader.
Hello everyone, and welcome to our 3rd Meet a Scientist event, which we have been conducting for all the Telangana Social Welfare Residential Schools for last 1 year. I know you must have been very excited to know more about our invited scientist for today's talk and also interact with him. But before doing that, I want you to think about something. So all of us uses a toothpaste every day, right? So have you ever thought whether the toothpaste is a solid or a liquid? I think you all must be thinking what I'm asking right now. So it is like, have you ever thought why the toothpaste stays in the tube as such and doesn't flow at all, but when we press it, it starts flowing. So what happens to the toothpaste? Don't worry, I'm not asking you to give the answer right now. Keep thinking, but at the end of the session, you will definitely have an answer for this. So without further delay, let me give a warm welcome to our invited guest for today's program. He is an eminent scientist from the Institute of Mathematical Sciences, Chennai, Professor Gautam Menon. So to just give a brief introduction regarding his background, Professor Gautam did his schooling in Kerala and Tamil Nadu and obtained his bachelor's degree in physics from Delhi University. He did his master's in physics from IIT Kanpur and PhD again in physics from the Indian Institute of Sciences, Bengaluru. Further, Professor Gautam did his postdoctoral research at Tata Institute of Fundamental Research, Mumbai, and also at the Simon Fraser University, Vancouver, Canada. He has been working at the Institute of Mathematical Sciences, Chennai for nearly 20 years now, and Gautam says that he likes to travel a lot. So welcome, Gautam. And we also have with us today Dr. Anu Joy. So she has a PhD in Science Education from the National Institute of Advanced Studies, Bangalore. Her research is in the area of cognitive ethnography of science learning. She holds an MSc in physics and works with children on science learning projects. Prior to her PhD, she worked as a researcher in the area of nuclear magnetic resonance spectroscopy at NMR Research Center of IISc Bangalore. Welcome, Anu. So before I hand it over to Gautam to start his talk, we would like to have a short discussion regarding his backgrounds and his interests. So Gautam, I would like to know what made you to choose science as a career?
As a child, I was always interested in science, of looking around me, looking at the world around me, and trying to understand a little more about it. So even at home, I used to do small experiments, small physics experiments, especially chemistry experiments. I used to like chemistry very much. And this interest grew until I finally decided that I wanted to pursue a life in science. And that's when I decided I should do a master's and then a PhD in physics. And now my interest has changed a lot even within physics. Now I work in many areas that are the interface of physics with other disciplines and other studies. Physics with biology is certainly one area that I'm interested in. Physics and medicine is another area. So that is really what drove me to begin to work in science.
Hi, Professor Gautam. Nice to meet you along with a large group of children. Maybe children would like to know a little bit about your present research. What is that you research?
So my main interests are now two. I work in the field of biophysics, which is the interface between physics and biology. It tries to understand biology from the point of view of physics, from the point of view of mechanics. and from the point of view of understanding how biological systems actually work and function. My other interest is a little more mathematical. It has to do with how diseases spread in populations. So that is an area where I think people like me who are interested in physics, mathematics, and applications of physics and mathematics can contribute a little bit to understanding social problems. For example, how do diseases spread? How do we control the spread of diseases? How do we ensure that there are no epidemics that take over and spread over the entire country? So that is another interest of mine, more specifically over the last few years. So I work in biophysics as well as in diseases, understanding diseases from a mathematical point of view.
Yeah, this looks very interesting. This is the first time children may be listening about, a scientist working in multidisciplinary areas. Children learn about physics, chemistry, maths, social studies, etc. in school. So can you further elaborate what is interdisciplinary work? How a scientist approaches interdisciplinary work?
So when we study in school, we think of chemistry as one subject, physics as one subject, biology as another subject, and mathematics as a totally different subject. But as we learn more and more, we realize that all of the stuff that we didn't know, much of what is new, novel, and exciting, actually happens at the boundary between these different fields. Between physics and biology, for example, is very interesting. We study biology mainly in a descriptive manner, but if we want to understand it from really understanding how the parts of a biological system function together, how something living can come out of atoms that are really non-living at their essential core, that's an interesting area for us to look at. When we think about materials, for example, that's an area that is very interdisciplinary between different sciences. There is the physics of materials, there's the chemistry of materials, and there's applications of materials. One example that Devashri mentioned just now was toothpaste. So that is an example where you have to combine the chemistry of how toothpaste is made with the physics of how toothpaste function, as well as the sensations that toothpaste are supposed to evoke in us when we brush our teeth. And all of these different things, the experience of a material, what a material is made up of, which is chemistry, and how a material functions, which is physics and chemistry together. These are areas that need many different people to work together, many chemists, physicists, engineers especially, to work together to understand how to make these properties of materials the way that we want to. And I will describe this as I go along.
Yeah, thank you. You also mentioned that you are working in an area of epidemics. This points us to the fact science can help the society. There is a lot of relevance for science to the society. Can you briefly share with children how your research is helpful to the society?
So one reason we began to think about diseases and how to model diseases and how to understand models of diseases that other people had written down was to try and understand in India how can we solve the problem that are Indian problems. And certainly disease in our population is a very major problem for us to be worried about and concerned about. And that is why we thought that trying to understand it, and try to be able to predict what might happen with specific diseases would be important for India in the future. So I think as all scientists do, we also have a part of us that is social. We would like to do good for our society. And it seems that with the training that I had, this would have been the area in which I could contribute most towards understanding a social problem and trying to understand how to solve that particular social problem.
Professor Gautam also worked in the area of statistical physics, condensed matter physics, and superconductors. So he's the right person to discuss with us about the concept of matter. Matter is a very fascinating area of study in physics, from the materials that make the everyday world to the subatomic particles, electrons, protons, tachyons, even Gauss particles. The everyday world of us is surrounded by a wide variety of materials. How this grand variety possible? What makes certain materials unique? Gels, powders, soft and pliable materials, non-rigid solids. How can we explain and understand the properties of everyday materials like honey, ghee, camphor oil? What are the physical properties of an ice cream? Welcome Professor Gautam to deliver the talk, The Physics of Soft and Hard Matter.
So let me begin by telling you that if you look around you, you will notice that you are surrounded by materials wherever you are. These materials can be different. They can differ in their physical, chemical, mechanical and other properties, but it's these properties that determine how useful they are. For materials that are man-made as opposed to natural materials, it's hard work to figure out what these properties should be and how to get these properties right. The examples that I want to describe today to you are ice cream and toothpaste as two major examples that you are very familiar with. Ice cream is a very interesting example that many of you would certainly have experienced or seen in your lives. And to understand ice cream and what makes up ice cream and the properties of ice cream is certainly something that is very interesting, and I hope you will begin to notice this in your life as you move onward. The second example that all of you are used to is toothpaste. Toothpaste again is something all of us brush our teeth every day, and we're familiar with the properties of toothpaste, but the properties are unusual, as I will explain a little bit later. Toothpaste is partly solid, partly liquid, and we have to try and understand how its properties are such that it can be both of these things at the same time. I will give you other examples as well: wood, bone, concrete, LPG that you get in your LPG cylinders, water, honey, tomato sauce. All of these are examples of unusual materials, and I will describe each of these materials as we go along. First of all, materials are all around us. So whether this is a famous picture in Hyderabad itself. So over here you can notice both a building, a large building, as well as people, as well as auto rickshaws that are on the ground. So there is a combination of stone or various different types of stone, as well as highly processed metal. The people who are walking around in that photograph are made of soft tissue, cells, etc. So just in one picture you can see both man-made and non-man-made materials. The next picture is a picture of a view in a village. Here you can see mainly things that belong to our natural world. You can see trees, you can see leaves, you can see grass, you can see fields. All of these have different properties. The trees must be strong enough to be able to withstand the wind, so they can bend in the wind, but they should not break. The same for the leaves and the crops that are planted in the field. The road that you see is made up of gravel of many different sizes. It is starting from very small sand grains to larger stones. So again, look around you and look at the diversity of experience that you can get when you just look around yourself and look at the world. Some things that you must certainly have learnt about is that some matter is hard. For example, crystals are hard. This is a picture of a crystal where you can see that the fact that it's a crystal is made clear by the fact that it has clean planes along which it is divided. So that's hard crystalline matter. The second picture is that of a glass with a flower in it. So the glass is also hard, but the glass is not a crystal. If you look at where the atoms are arranged inside the glass, they're not arranged in any regular order, they're arranged in slightly random order. Okay? So this is material that can both be hard as well as not a crystal. The third picture is one of a material that we see all around us every day. That is a set of plastics. So there is plastic in almost everything that we see. This is plastics in bottles of water that have been discarded. These materials have many uses. Plastic is very long lasting. It can be changed, its shape can be changed and fit into a variety of different shapes. And the problem with plastic is A, that it is very useful, but also that it is long lasting. And one worry that we have now is pollution that is caused from the fact that plastic does not easily decay over a short time. This is an unusual example of a flexible material. I don't know if you've thought about this, but your ear is an example of something that is very flexible. You can take your finger, bend your ear or your friend's ear, and even then when you release your finger, it will come back into its normal position. So your ear can be very flexible and yet able to return without being deformed into its natural position when you finish bending it and release it. This is an example of a fluid, of a wave in an ocean. You can see now that the atoms here are not solid-like. That is, they don't have a precise arrangement with respect to one another. They're not like a glass, which is still solid, but the atoms don't have an arrangement that is predesigned with respect to each other. And it's also not like the other example. It's not like living matter, but it's something that flows. For example, you're used to thinking of liquids as objects that can fill the shape of a container. So here is an example of something, again in our natural world, which is fluid-like, meaning that it can flow. To go back to where all of these materials came from, let me remind you that all of matter is made up of atoms. hydrogen, helium, carbon, nitrogen, oxygen, all of these are basic atoms. These atoms combine together in specific chemical ways to make molecules. And this is a picture of some of the atoms and some of the molecules that are made by these atoms. These atoms, if I take the same set of atoms, for example, atoms of water, H2O, they can exist in many different states. And these are states that you are familiar with from your school. They can exist in a solid state, for example, like ice, which is a crystalline solid made up of water molecules. It can exist as a liquid, which is water as we know it, but it can also exist as a gas, which is when we apply heat to this water, it can vaporize and form water vapor. So the same atoms, whatever they might be, can exist in very many different types of states, solid, liquid, and gas being the states that we are familiar with. So the properties of the materials that you see around you depend on what are the atoms that they're made up of. But they also depend on how these atoms are connected to each other. Are they simple molecules like the examples that I showed you in the earlier slide? Or can they be long and complex like polymers? One example of a polymer is DNA, which you may have heard about. It is a long molecule made up of units that are added on top of each other. So this is called a polymer. The other thing you could ask is the material made up of many different types of molecules? Are there long molecules and short molecules? Are there molecules of water and molecules of carbon dioxide? This would take us to the idea of a composite material, where you can have a material that is made up of taking other elemental and molecular materials and putting them together. The last example of it is, can a material be solid, liquid, or is it possible to be both solid and liquid at the same time? And we'll look at some examples of such unusual and interesting materials. So here is an example of a bunch of different types of arrangements of materials. We start in the top left hand corner with an atom. We have a molecule which is made up of atoms. We have polymers, which are long molecules. The example to the right hand side is that of a carbon nanotube, which is really a long molecule made up of carbon in a very special tube-like structure, which is why it's called a nanotube, because the tube can be extremely narrow. If you look to the left of that, that is the example of a crystal, a polycrystal, and an amorphous material. A crystal has atoms arranged in a very regular way. A polycrystal has arrangements of these atoms in a regular way, but they don't fill up all of the space. There is one small little crystal over here, there's a crystal next to it and a crystal next to it, but they don't link up or tie up together so that all of the space is occupied. And then I mentioned amorphous materials like glass, where the atoms are not arranged in any sort of regular way, either like a crystal or a polycrystal, but they're arranged in a somewhat random way. But even then, they can behave as though they are a solid material. The example below is that of a complex fluid, which is a fluid, a liquid, with many different types of molecules inside it. Some could be long, short, or just different types of molecules. And the example on the right is the example I will tell you a little bit about now, which is complex solids or composite materials. So let's begin with a composite material, and here are two examples of what are composite materials. On the left is wood, and on the right is a bone. Wood is a composite material. It's made up of cells, both living and dead cells, but the cells are made up of substances called cellulose, which is the majority of the material, lignin and hemicellulose. So cellulose is really the bulk of the tree. It's lignin that holds these fibers together. On the right hand side you can see bones, an example of a bone. The bones in your body are also composite materials, that is, they're made up of different types of solid materials. So bones are made largely from a brittle material called hydroxyapatite, which is mainly calcium phosphate, but it's also a soft and flexible material called collagen. So it's a combination of a hard and a soft material together that give the bone its very special structure and strength. The other composite that you might know about is concrete. Concrete is a mixture of small stones, of cement and sand. If you add metal rods or wires to the concrete, you can make it much stronger, and this is called reinforced concrete. The first modern composite material, remember that concrete is an old material. For many years, mankind has been building materials with concrete. But the last example is that of fiberglass, which is a modern material. Okay? And that is also a composite material. So here's an example of how wood and reinforced concrete are alike at a basic level. Remember that I said that the wood has cellulose running through it, and the cellulose is tied together by lignin. Similarly, in reinforced concrete, the steel bars are like the cellulose, and the concrete that ties them together is like the lignin, together forming reinforced concrete. Here's a second example, again one that should be common knowledge to all of you. And that's the example of a gas. And in this example, it's gas that comes out of a burner. So LPG, or liquefied petroleum gas, is produced during natural gas processing and refining. And these gases are propane and butane in India that form our gas cylinders. It's liquefied because it is liquid. When it is poured into the cylinder, it's liquefied by putting high pressure on it in order to make it stored more easily. If you release the opening to the cylinder, the liquid then boils and turns into the gas that is then released through that narrow opening that you see at the top of your gas cylinder. When you release the pressure by turning on the stove, this gas is then released. When the gas is burnt, you get a blue gas flame, as long as there's enough oxygen for the gas to be burnt completely. If there's sufficient oxygen, the gas flame appears blue. If it doesn't, it can appear yellow as well. And it's complete combustion, that is the interaction of the burnt gas with the oxygen present in the atmosphere, that creates enough energy to excite and ionize the gas molecules inside the flame. Now let's move from solids and gases into liquids. So here is an example of a liquid being poured into a glass. And as I said, the interesting feature of liquids is that they can be poured, they flow, they take the shape of the container that contains them. On the right side, you can see an example of water coming from a tap, dripping, and next to that is honey flowing from a stick. You can see that the honey flows much more slowly than the water, which moves much more fast. So liquids can flow and solids can't. Liquids take the shape of their container, but the important feature of liquids that separates one liquid from another liquid is that different parts of the liquid don't like to move at different speeds. And the property that ensures this is called viscosity. It's viscosity of the liquid that tries to make the speeds the same in different parts. So the main difference between water and honey, apart from the fact that they're very different chemically, is that they're liquids of very different viscosity. So here's an example of how viscosity appears in a practical context. If you take a ball and drop it through a liquid of different viscosity, so on the left is a liquid with very different viscosity, very small viscosity, and as you move towards the right, it's liquid with more and more viscosity. You can see that the ball is moving slower and slower. It takes more and more time to reach the bottom of the container if you put it in a liquid with more viscosity as opposed to a liquid with less viscosity. And again, as I said, this basic property comes from the fact that molecules in a liquid don't like to move relative to each other. And the more viscous they are, the more they dislike moving with some velocities relative to each other. Here is an example of something that again you will have seen. This is a ketchup bottle, okay, a bottle of tomato sauce. So what are the properties of tomato sauce that make it special and unusual? So here is an example. It shows somebody walking through a desert, finally finding a bottle of tomato sauce, putting it in their mouth, but the sauce doesn't come out. They shake the sauce and shake the sauce until finally the person dies because the sauce is not coming out of the bottle. And only then you can see now that the sauce has begun to come out of the bottle, but by then the person is dead and only the skeleton is left behind. So this is a funny property of the tomato sauce that all of you must have seen. If you shake the bottle, you have to shake it and shake it in order to let the sauce flow. If you don't shake it, even you can tilt the bottle and the sauce is very reluctant in order to come out. So the property of the sauce is that before shaking it, it is held together by bonds between the different molecules inside the sauce. And these bonds hold its shape together, and then it behaves like a solid. By shaking the bottle, I break some of these bonds that hold these molecules together, and I allow the molecules to move with respect to each other. But moving with respect to each other is a property of molecules in a liquid. So as I shake it, I make it more and more liquid-like, and that's when the sauce begins to flow. So the two words that you need to understand is, one is a word called yielding. Yielding means that I must apply a certain amount of force to the material before it begins to flow. And the second, more technical word is called thixotropy. And thixotropy means once it flows, it begins to flow easily and more easily as time goes on. So this is precisely the property that sauce has that makes it special. Let's come to another example, which is the example of toothpaste. Again, this is an example that all of you must have seen. So the properties of toothpaste are unusual. Because inside the tube, a toothpaste must behave like a solid. If I open the cap of the toothpaste and hold it upside down, this toothpaste must not flow out. On the other hand, if you squeeze the tube, then you want the toothpaste to flow out. So without squeezing, the toothpaste behaves like a solid. Once you squeeze, the toothpaste behaves like a thick liquid. The second part to it is, once it reaches your toothbrush, once you put the toothpaste on your toothbrush, you don't have to worry about it flowing off the brush as you raise it to your mouth. So it must become solid once more and not liquid anymore. So the word here to understand is a word called yield point, and that measures the force that you must apply to a toothpaste tube before it starts to flow. So below the yield point, for example, if I'm not applying any force to it, the toothpaste does not flow out of the tube if no force is applied. So it must behave like a solid. But above the yield point, the picture on the right has a much larger force applied to it, a much heavier object placed on top of it, and then the toothpaste begins to flow out of the tube. Let's talk a little bit about the special properties of toothpaste. If you don't brush your teeth, then remember that your teeth decay because bacteria form on your teeth. So bacterial biofilms called plaque build up on your teeth every 12 to 24 hours. What toothpaste does is to make the brushing more effective because it contains abrasive materials or rough materials. In addition, toothpaste must foam because it contains what is called a detergent or a surfactant, which is another type of cleaning ingredient. What these ingredients do is to loosen and break down the substances on your teeth that would otherwise not be dissolved and rinsed away if you just wash them with water. So there are other ingredients that must be part of your toothpaste. For example, these must be ingredients that retain moisture because you don't want your toothpaste to be dry. You must also keep the different ingredients in the toothpaste from separating out. Okay? The third part of it is toothpaste also needs flavoring. Natural and artificial flavors and sweeteners such as saccharin are also added to the toothpaste. So it's the foaminess of the toothpaste, the abrasive nature of the toothpaste, as well as the sweetness of the toothpaste, all of which go into making brushing the experience that you enjoy when you brush your teeth in the morning. The other example that I want to tell you about, that is again an example from food, and that's an example that all of you know about. This is an example of ice cream. So ice cream is a complex material. It contains water, it contains sweeteners, it contains flavorings, emulsifiers, stabilizers, milk fat and milk solids. And on the picture on the right, it blows up some of these parts. It shows you the air that is contained, the crystals of ice, the globules of fat, as well as some of the chemicals that are added to it, including sucrose, as part of the liquid syrup that accompanies the ice cream. Ice cream is technically called an emulsion. An emulsion is a combination of two liquids that don't like to mix together. And in this case, it's liquid particles of fat or flat globules that are spread along with a mixture of water, sugar and ice together with bubbles of air. Now fat doesn't mix well with many other substances. Just if you add oil to the water, they don't mix together. The fat content in the ice cream has a tendency to become separate. Okay? So you should think of ice cream, as I said, as air bubbles and ice crystals in water together with fat and other substances that hold all of this together. So what you must add to make sure that ice cream doesn't separate out, one important chemical is called an emulsifier, also called a surfactant. This makes the emulsion, which is a mixture of oil and water in this case, stable. It prevents the droplets of fat from clumping together and separating out. They also act like sponges, holding into place any liquid in the ice cream. Finally, stabilizers keep the material uniform, keep the texture creamy. They prevent large ice crystals from forming. And once you add a stabilizer, the ice cream contains small crystals that melt more slowly. And if you look at the ingredients of an ice cream, you will see words like gelatin, guar gum, xanthan gum, carrageenan. All of these are stabilizers that help to keep the texture of the ice cream uniform. Usually a lot of sugar is added to ice cream, sucrose or glucose. And here an interesting point is that cold numbs your taste buds and makes them less sensitive. To make up for that, you have to add even more sugar so that you taste the ice cream as being sweet at the temperature at which you put it into your mouth, which is fairly cold. So if you take the ice cream and heat it up to room temperature where it becomes a liquid, it tastes really sweet. But that's because it is really sweet. A lot of sugar has already been added to the ice cream. So the crystals that form in ice cream feces are very important to the quality of the ice cream. So smooth ice cream needs very small ice crystals, and in order to get small ice crystals, you need to freeze the ice cream very fast. However, even then, you still have ice cream mainly made up of water with respect to ice. When you serve it at usual temperatures, not all of this water is frozen, and it's this that allows you to be able to scoop up the ice cream together in an ice cream scoop. My last few examples are somewhat different examples and have to do with color and how you perceive color. Remember that the surface of an object reflects some colors but absorbs other colors. What we see is only the reflected colors. So you see a blue object because it absorbs all of the other colors of the white spectrum and reflects only blue. You see a red object because it absorbs all of the other colors of the white spectrum, which is the whole spectrum of colors from violet, indigo, blue, green, yellow, orange and red, but sends back or reflects only the red objects. Similarly, a white object takes all the color in and sends all the color out. And a black object absorbs all of the colors that are incident on it and doesn't reflect any other color. Now you can ask, what determines unusual objects that seem colored? So here is an example of a bee that has a very striking and remarkable color. It's not a color that you normally see. So now you can ask, I see beetles in many places. What determines their unusual coloring? It turns out that it's not the simple way that things are colored. Beetles are colored because their outer surface has many stacks of small plate-like layers which point in different directions. It's these layers that bend and reflect the incoming light. And in addition, there could be more pigments that make this effect a somewhat larger effect. So let me give you this example of, this is really what the different layers look like. In this case, it's called a diffraction grating that takes in white light and sends out light. But the light that it sends out is broken up into different colors depending upon what the wavelength of the light was. So you can see the blue, the green and the red all split out separately. The same principle unusually also holds for the surface of a CD. A CD has very, very small little microscopic bumps, just like the diffraction grating that I showed you, and also like the surface of the beetle. It's the same colors that you see on the surface of a CD that are also like the colors, the strange iridescent colors of the beetle. So here's an example, both from our technology and from natural technology, of how these very bright and interesting and remarkable colors can be obtained by looking at the structure of a particular material. So what I did here was to show you many examples. We started with wood, with bone, with concrete, with fiberglass and LPG. These are all, some of them were solid materials, like some of them were composites like concrete and fiberglass. Some were gases which were made from liquids like liquefied petroleum gas. Then we took the example of water and honey, which were liquid in nature. We looked at tomato sauce, we looked at toothpaste, then we looked at ice cream, and finally we ended up with thinking about beetles. I just chose this set of examples as examples that you would see every day around you. And that's what I want to emphasize in this lecture that I have given you, that just by looking around you, outside your classroom, inside your classroom, at the many, many remarkable things that you see both at home and at school, you can understand a whole lot about the world by just thinking about materials, what makes these materials what they are, what determines their function, and how interesting they can be. So now it's your job to think up interesting materials, to think of their functions, and think of how they accomplish what they do just by looking around you. And if I have conveyed this to you, I would be very happy.
Thank you, Professor Gautam, for guiding our attention to the wide variety of materials that surround us and showing us the potential of learning from everyday world, even while enjoying an ice cream or being in the near the ocean. The talk really showed the everyday world is the most potential source of learning, and you really guided our attention to a variety of materials that we never kind of given a thought also. Thank you so much. Now we will have questions from children. Children were listening to your talk, and we will take a couple of questions from the children.
Okay, I think Till we get some calls from students to get questions. So I would also like to thank you for making us visualize science all around us. Maybe I would say usually what we feel that science is something which is only located in a particular lab, and it is something beyond the reach of general public. But your talk today made all of us know that science is all around us. We just have to look, and we have to find the reason behind all the things happening, and even the matters, as you have just pointed out in your talk. And that's really, I hope the students must have enjoyed your talk a lot. Thank you, Professor Gautam, for such a wonderful talk.
Still we wait for children's question. Can I ask you just one question? Can you elaborate a little bit upon the properties of powders, which we were not able to discuss much in the present talk? What are the properties of powders, and what are the interesting properties that we can...
So powders, or what are called granular matter, have many interesting properties, and certainly sand is a very important part of modern technology. It goes into concrete, and you can see the sand piles that are formed when sand is piled up on top of the surface of a road. So one question that is interesting is what determines the shape of these sand piles. If I add one more grain of sand to the sand pile, where does that grain go? Does it set off many sand piles? Do they begin to move? The other example of material that is granular is the example of rice or grain that is stored in a large silo. And here, for many years, people were mystified or surprised by the fact that the silos would spontaneously explode on their own just when material was stored in it. And it took some years for people to understand that the nature of the material itself and the forces that it exerts on what is confining and what is surrounding it is important, is very important in the case of granular media. And one other very nice example that I can think of is the example of the hourglass, where you take two containers and you connect them through a narrow little opening here, and that enables you to tell time by just turning the hourglass over and watching the sand flow through. If you look at this, the sand must flow through at a precise rate. It must not get stuck or clogged, and by the time all of the sand from the top has come to the bottom, then the time of 1 hour or half an hour or 20 minutes or 5 minutes must have elapsed. So the sand must have very special properties in order to do so. For example, with water, it doesn't quite work like that. The rate at which water flows will depend upon how much water there is and how much pressure is exerted by the water above. So these are all very interesting features of sand. For example, sand, grains, granular media, how they pack together, that excite and interest physicists especially, but not just physicists, but also engineers working in many different areas of engineering.
So another area where the students were very much curious to know about was regarding foam. So they wanted to know whether foam can lead to, there's some state transition occurring in foam, or what happens. In fact, they wanted to know that whether foam can be solidified to make a sponge or something like that. So, what do you can you explain, or scientifically can you tell something about the properties of foam? And
so foams are really bubbles of a gas, surrounded by a thin layer of liquid. And as this liquid flows through, the smaller bubbles give way to the larger bubbles. They flow, the air flows in from the smaller to the larger, and the structure slowly becomes bigger and bigger. One way to make foams, of course, is to add solution of detergent solution to water and then stir it a lot. And this gives you bubbles of many different sizes. The bubble itself is an extremely interesting structure, a single soap bubble, because its shape can, if you look at a single soap, you can see that just the small pressure of air from side to side can make these large changes in the shape of the bubble. So mathematicians are very interested in the shapes of bubbles, what determines those shapes. Physicists are interested in bubbles because they want to know how do these bubbles coarsen, how do small bubbles give way to larger bubbles, how does the bubble structure become larger, what determines the physical laws that govern these bubbles. And of course bubbles and foams are very interesting from many other different points of view. For example, in engineering, foams are also an extremely important part of how we think about. So the combination of oil with a solid structure, of gas with a liquid-like structure around it that helps to protect it, could also be a combination of a solid of a gas with a solid-like structure, as you said, like a foam. And certainly there are ways of chemically modifying the liquid so that it can become more rigid and structured and held in place. So the combination of both an air and a sort of semi-solid structure around it is certainly known.
So the foam can be engineered to make it
you can engineer foams to make them more solid-like as opposed to liquid-like.
You have mentioned about materials that are in between solids and liquids. We have everyday examples of butter, ghee. So how we can understand such materials? What properties give them that such kind of a structure? Also, another interesting material may be gels. Can we explain toothpaste, gels, ghee and butter with the same explanatory structure?
Yes, because all of these you can think about the general term called a complex fluid or a complex liquid. This is a liquid with some structure inside of the molecules. The examples that I gave you, both of tomato sauce as well as toothpaste, toothpaste is a very good example, because toothpaste, in order for toothpaste to flow, I exert a certain amount of force on it, but once it flows, it acts like a liquid. So this is the same principle that goes into determining many complex liquids. For example, butter, as you said. Butter is something that that could be either a solid, depending upon if it's in the fridge, where it's solid-like, but once it begins to melt, it's both a combination of a soft solid that you can change and deform, as well as a liquid part, which is the melted butter. All of the examples, even the batter with which you make the idli or the dosa that you make at home, that's also a complex fluid. You can move it around. You can take a spoon and move the batter around. You take the spoon out, it stops flowing. This is again unlike a normal liquid, where if I take water and move my spoon around, the water keeps flowing around for a little while until it begins to slow down.
I think we are getting a call from a student, so we'll take up the call now. Hello.
Hello, good evening, madam.
Yeah, good evening. May we know your name, please? From where you are calling?
Ganesh, madam. From Narangere.
From which place?
Narangere, madam.
Okay, so what's your question?
My question is, what is the relation between hard and soft materials with physics?
Hard and soft.
If I hear it, what is the relationship between hard and soft material in physics, right?
Yes, ma'am.
Yeah, no, it's the same distinction as exists in your own experience. Materials that we call hard are materials that are very difficult to deform or change the shape of. For example, if I take a block of metal, it's very hard for me with the forces that I exert upon it to change its shape. If I take a piece of rubber, for example, or a straw, or for example, the example that I used was the example of a ear, those are materials that are soft and flexible. They can be moved around. You can change their shape. So the same feeling that you get when you see these materials and what they do when you deform them is very similar to how we think about it in physics. What is soft and what is hard.
So we are having another call. Hello.
Hello. Good afternoon, ma'am.
Yeah, good afternoon. From where you are calling? Yeah.
This is Nitya from TSWREIS Armour.
Okay. So what's your
My
question?
is, what is the properties of cosmetics like Fair and Lovely and creams?
Properties of?
Can you please repeat your question one more time?
What is the properties of cosmetics like Fair and Lovely and...
Okay, so she wants to know about Fair and Lovely and the
no,
creams.
That's a very good question, and many people work very hard, engineers, scientists, physicists, chemists, on making those creams in exactly the right way. The same problems that there are in making creams also are there in the example of toothpaste. You must make sure that all the different chemicals that you add together remain together, they're stabilized, so it's one common cream that you can scoop up in order to use. This is usually somewhat hard to do because many of these chemicals they prefer to sit together, they don't like to mix up together. So you have to look in detail at what are the components that go inside Fair and Lovely, etc., in order to figure out what did the chemists do in order to make that hang together. And of course, with cosmetic material, they must also have a function. For example, which you might have a fairness cream, would want to remove some set of dead cells from the top. That would be one function of that. It must, in general, creams and shampoo must smell nice. So you must add additional fragrances in it in order to make it behave, make it smell the way that you want it to smell. It must have the right texture. For example, you should be able to take the texture off, you should be able to take it off and wipe it on your hand or your face or your body. So these are all important ways in which these materials must be designed for the particular function that they must satisfy. And an important part of that design is just making sure that the material stays together and doesn't separate out into its constituents.
Thank you, Gautam. We have our next caller. Hello. Hello. Okay, so there's some problem. So maybe. Okay. Hello.
Hello, madam. Good evening.
Yeah. Good evening. So, can you introduce yourself?
Madam, my name is Sai Vamshi Krishna. I am from Sirpur town, Kagat Nagar.
Okay. So, what's your question?
So, my question. What is meant by plasma state?
What is meant by plasma state? So the plasma state is sometimes called the fourth state of matter, and we had solid, liquid and gas. But the plasma state is one in which the atoms that are there in a gas state have now begun to spread out into their nuclei and the electrons on the outside. So in that case, the electrons are moving around, the nuclei are moving around, but they don't move around together as they would in a normal neutral atom. This state is special in many ways because all of this charge is moving around. If you look at the outer parts of the sun, you have matter that is also in a plasma state. Much of it is just electrons and the nuclei of hydrogen moving around separately from each other. You can also make plasmas in the laboratory. You can, by going to sufficiently high temperatures or hitting atoms against each other. That is why it's called the fourth state of matter. In a sense, it is like a gas because the atoms are moving around at random, but you've broken up the constituent atoms of the gas into electrons, protons and neutrons.
So we have our next caller. Hello.
Hello.
Yeah, please go ahead.
I'm Lavanya.
Okay. Lavanya, what's your question?
Can we produce electricity by creating movement between any two solids?
I'm sorry, can you repeat your question a bit slowly?
Can we produce electricity by creating movement between any two solids?
Can we produce electricity
by creating movement between solid and a liquid?
Okay.
Between solid and a liquid?
Yeah.
That's a very interesting question, and there are some examples where people know that it can be done. For example, if you take a liquid and flow it over what is called a carbon nanotube, you can generate a potential difference between the two ends of the nanotube. And I think there are other examples as well. Relatively less is known about these examples, both from a physics point of view. And that's a very interesting question to ask. Is this one way in which you can get a potential difference by just flowing a liquid across a solid?
Okay. So I think we have you have answered all the questions right now. So maybe we can move ahead with the formal concluding remarks from Dr. Anu.
It was a very interesting session. Thank you to all the children who came up with the questions. We are awaiting for more questions from you. You can send all your questions to us. We will be very happy to answer all those questions. Thank you, Professor Gautam. Thank you, Debashri. Thank you so much.
Thank you.